All right, guys, we're picking up where we left off with QC and how it relates to KC. And we have a question 17.24 on the homework. So, guys, now that I got the correct stream code in, I could flip back and forth between the PowerPoints and the live webcam using my OBS software. So I'm doing, instead of posting the whole entire live stream, I hit record now so that we can have our lecture and then we can talk after the live stream, and that's all not, clogging up the stream if you need to, or the video if you need to look back. So it says, as an EPA scientist studying catalytic converters and urban smog, you want to find the KC for the following reaction. So we want 2NO2 gas. Is the microphone fine? Can you hear me all right? I'm still waiting for my microphone to be delivered from Amazon. But is the volume all right, guys? So 2NO2 gas yields N2 plus 2O2 gas. All right, give me a second here. Yields N2 plus 2O2 gas. All right. And they give you a couple of formulas here, or a couple of equations, I should say. Come on, fingers, work. All right, and they say using the following equation. So 1/2 N2 plus 1/2 O2 yields NO. (4.8 times 10 to the negative 10th). And 2NO2 gas is at equilibrium with 2NO gas plus O2 gas. 2NO gas plus O2 gas. 2NO plus O2 gas. And the KC is 1.1 times 10 to the minus 5th. All right, so here's what they give you. Okay. Here's what they give you. And they want this equation down here. So that's what we're shooting for. All right. I have the microphone up. How about now? Can you hear it better now? All right, cool. I don't want to blast it out here. All right. So we want this equation down here. We have these two up here. Okay. So we got to decide what we need to do. So first thing is make sure everything is on the correct side using these two equations. Okay. NO2 is on the correct side. It's here, we're okay. We don't have to flip that equation. N2 and O2 are on the incorrect side. They're on the reactants in this, and in our reference equation, they are on the product side. So we need to flip this top equation. That's our first step. So we'll have NO gas is at equilibrium with 1/2 N2 plus 1/2 O2 gas. Now, if we flip it, the Kc becomes the reciprocal. So the new Kc becomes 1 over the 4.8 times 10 to the minus 10th. So that's our first step. Make sure everything's on the correct side. So now our N2 and our O2 are on the correct side. Our NO2 is on the correct side. By flipping it, your Kc becomes the reciprocal. Now, our next step is to make sure we're in the same ratios as we are down here. So I've got two NO2s. I've got two NO2s. I can't pick up an NO2 anywhere else. So this one is all right. This equation is okay. We're not going to touch that one at all. Everything's on the proper side. And the NO2 that we're worried about is in the right ratio. We do have an O2 here, and we need two of them. But we only have one, and we know we can't touch this because if we change this, then this is going to be wrong. So hopefully this O2 and this O2 add up to two O2s. If we look at the numbers here now, I need a full mole of N2. I've got a half a mole up here. Therefore, I need to multiply this reaction by 2. So this will become a 2. This will become a 1. This will become a 1. And I'm going to write this Kc down here so you can see it. Okay, I'm going to bring this down here. So, I already did the reciprocal because I flipped it. So I already have, for the new equation, 1 over 4.8 times 10 to the minus 10th. What I then need to do, since I multiplied by 2, the rule is you then take the Kc to that power. Now, we need to cross things out that could get crossed out. Well, the only thing that could get crossed out is the two NOs, which is good because we don't need them. So what are we left with? We're left with two NO2s, that's good. We're left with one N2, that's good. We're left with one O2 in here and one O2 down here. So if we added these equations together, 2 NO2 on the reactant side, 1 N2 on the product side, 1 plus 1, 2 O2s. You could, Victoria, it's the same exact thing. It's the same exact thing. Raising the 4.8 times 10 to the negative 10th to the negative 2 power is the same exact thing. I'm just showing the steps where you would flip it or raise it to the negative 1, but I try to take as much math out of it as possible and say, well, raising it to the negative 1 is taking the reciprocal. Now, to find our Kc value for this reaction, I've got to multiply these two values together. So I've got to multiply this value by that value. And whatever you get, I don't have... Do I have my phone even on me here for a calculator? That's the one thing I didn't pack up out of my office. I have 4 calculators sitting on my desk. So, let's see here. 4.8 exponent negative 10. I raise that to the negative 7. What's that? Square that. And then multiply it by 1.1 times 10 to the negative 5th. I get 4.77 times 10 to the 13th. That's my answer. So what does this value tell us? This value tells us that the formation of NO2, that the reverse reaction, okay, at equilibrium, all right, that the products are favored. So this reaction, the reverse reaction, is not, and the decomposition of NO2 is favored. Products are favored because the Kc is a lot bigger than 1. Okay. No, it doesn't. Since you're multiplying them together, Kelly, I saw your second question there. Does the order matter? No, because you're multiplying them together. So it really doesn't matter. Let's see. 1. Is there... If there's a compound that is AQ, do you include that in your reaction? Yes. AQ and gases are in your reaction, your Kc or your QC. Liquids and solids are not. But AQ is an aqueous solution, so yes, that is included. Yeah. I know this looks a little crazy right now, but do you have any questions on this? Guys, I'm working through your take-home exams too, so I'll get them done probably by the weekend. So I'm still trying to organize everything for this these lectures and everything. All right, more homework questions. Do we have any more questions? All right then, so where we left off was right here. We calculate QC and K. Question. All right. 17.17. Gotcha. Let's see, 17.17. A particular reaction at a temperature has a Kc of 6.5 times 10 to the second. Okay, so this is 17.17. And, all right, so 2NO gas plus 2H2 2 2NO gas. 2NO gas plus 2H2 gas is at equilibrium with N2 gas and 2 waters. Kc is equal to 6.5 times 10 to the second, which means the products are favored. Big Kc, products are favored. And then it asks the following. What would the Kc for the following be? So, letter A says NO gas plus H2 gas is at equilibrium with 1/2 N2 plus H2O. Alright, so what we have to do here is compare the two equations. We've got to compare this equation to that equation and realize what has been done. Well, we have 2, 2, 1, 2 as our ratio up here. Here, it's 1, 1, 1/2, 1. So that means that this equation has been multiplied by 1/2. This top equation has been multiplied by 1/2 to get this equation down here. If that's the case, if we multiply a reaction by a value, then it's Kc to the n. So to answer that one, we need to take the square root of 6.5 times 10 to the second squared and raise it to the 1/2 power. For letter B, the equation is 2N2, so let me use a different color here. 2N2 gas plus 4 H2Os yields 4 NO gases plus 4 H2 gases. So if we compare this first red equation to this blue equation, the first thing I notice is that it's flipped. So it was flipped, which means that I have to do 1 over my Kc, which is Kc reverse or Kc prime. The second thing I notice is that everything's been doubled. 4, 4, 4, 2. So that's our Kc to the n, where the value is squared. So our answer, and you could do it two ways, would be, essentially, we have to combine the two, would be 1 over the 6.5 times 10 to the second, and then we square that whole thing, or 6.5, which is the same thing, times 10 to the second raised to the negative 2 power. Yeah, there's no such thing as division, so you use multiplication. So that's how you know what to raise to your power. Yep, always multiply, never divide. All right, any other questions? Yes, multiply by the reciprocal, never divide. $17.16. All right, so same idea. So let's look at what equation they give us. 2H2S gas at equilibrium with 2H2 gas plus S2 gas. Okay. At equilibrium with 2H2 gas and S2 gas. And the Kc value is 1.6 times 10 to the negative second. All right, there's our reference equation. They want to know what would the Kc be if we did 1/2 S2. Oh, this is 17.16, by the way. What was it? 1/2 S2 gas plus H2 gas is at equilibrium with H2S gas. So we got to compare the two. Okay, well, we'll do A and then we'll do B. We'll do A and then we'll do B. Okay. So we compare the two. First thing we notice, it's flipped. So that's going to be Kc reverse, or 1 over the Kc value. We also notice that we have multiplied everything by 1/2. We've multiplied this equation up here by 1/2. Okay. So that means we have a Kc to the n situation where 1/2 is our power. So our answer is essentially 1 over the 1.6 times 10 to the negative second raised to the 1/2 power. Because we need to flip it, so 1 over Kc, we need to raise it to the power, so we get that. The second one says, all right, 5H2S is at equilibrium with 5H2 gas and 5 over to S2 gas. I think it said S2, right? Yeah. All right. So the question is, I didn't flip it, but I obviously did change the coefficients. What did I change the coefficients by? And if you don't realize it here or here, it's kind of given away. Like, how did I get 5? What times 5, or what times 2 gives me 5, which is 2.5. But if you look here, since this is a 1, it kind of, this coefficient gives away what I multiplied the equation by. So in order to get this to be 5, I need to take 5 halves multiplied by 2 would give me the 5 coefficient in front. So if I have a coefficient of 1 and something looks funny here, whatever's in front of that coefficient is what I multiplied my equation by. So all this is, they try to trick you here, is a kc to the n, where the n is the 5 halves. So it's 1.6 times 10 to the negative second raised to the 5 halves power, or raised to the 2.5. Yep, they just try to trick you to make it look funny. But when in doubt, you have an odd number with an even number. Put the even number on the bottom, the odd number on top, and it'll work out. All right, anything else? All right then. So let's try again. Here's where we left off, comparing, or what is the difference between QC and KC. Remember, they're calculated the same way. Concentration of products raised to their coefficients times the concentration of reactants raised to their coefficients. Okay. If QC is calculated, it can be calculated any time during the reaction. At time 1 second, at equilibrium, right before equilibrium, way before equilibrium. Kc is calculated at equilibrium. So if we have two values and we're trying to figure out, okay, what direction are we going or what's going on, and we know the Kc value and we're given known concentrations, we can compare and know which direction the reaction is going by calculating the QC value. If my QC value is less than my KC value, we're going to move from reactants to products to get to equilibrium. If QC is equal to KC, we are at equilibrium. And if QC is greater than KC, that means we have way more products than we do at equilibrium, so then we have to move from products to reactants or right to left. So in an example, let's just make up a general example. If I had a reaction, okay, and it was, let's say, 2A gas plus B gas is at equilibrium and gives me 3C gas. And we said that the KC value is, I don't care, 2.2 times 10 to the second. And I said to you, when we measure the concentration at some point in time, okay, at some point in time, we'll say at time t, okay, the concentration of A is equal to 0.852. The concentration of B is equal to 0.367. And the concentration of C is equal to, I don't know, 0.984. And I want to know which direction is this reaction going, or is it at equilibrium? So am I at equilibrium? And if I'm not at equilibrium, which direction is the reaction going? Okay, so here's my equilibrium constant. Here's my concentrations at some time that I measured them. So what I need to do is set up a QC. QC is equal to the concentration of products raised to their coefficients over the concentration of reactants raised to their coefficients. So in our case here, it'll be the concentration of C cubed over the concentration of A squared times the concentration of B. If we want to set it up with the actual numbers, 0.984 cubed over 852 squared .367. Okay. So again, we got to calculate this. Let's see, 0.984. And I get an answer of 3.58. My QC is equal to 3.58. Okay, if I did the math right there. Double check me on it, but if that's the case, my QC is a lot smaller than my KC. So if we go back to the PowerPoint, my QC is smaller than my KC. I must be moving from my reactants to my products. I've got a lot more products at equilibrium than I do at this time that we recorded these concentrations. So I must be moving to return or to turn over these reactants into products. And that's what our QC is used for. Okay. It's calculated the same exact way as KC, except KC is specifically at equilibrium. Questions on that? What we're using QC for? Alright, so these were writing our QCs and things like that. I assigned these for homework. So we'll go through them really quick here. And let me get to, yes, right here. So this is a little summary of essentially finding QC and KC and how they work. So you have your first equation left to right, products over reactants raised to their coefficients. If I want to know the reverse, it's the reciprocal. If I'm going to, use two reactions to get a new one, then I have to multiply them together. If I change the coefficients by some value, I raise the QC or KC to that value. This is right out of your book, table 17.2. All right, so there's another constant value that's used specifically for gases. Okay, if there's gases in my equation, like this one up here. So I'm just going to get rid of this down here, like so. We'll leave that Kc value there. We don't need it right now. But there's another value known as Kp. Now, Kp is the equilibrium constant due to pressure, and that's why gases play a role in this. And it would be the same exact thing. It's the pressure of the products raised to their coefficients. I don't want to use brackets because that's concentration, so let's make a parentheses. Round out those brackets. Over the pressure of the reactants raised to their coefficients. Okay. So I would need the pressures, or to make it even better, okay, we're going to bring back our friend PV equals nRT. So what if they gave us this equation up here and they said, well, here's the temperature, right? Here's the number of moles that's in the interaction. We can figure out what the pressures are to find Kp. So that can be done, but what's usually done is relating Kp to Kc. And it is related in a formula that is basically PV equals nRT. The formula that relates Kp to Kc is Kp is equal to Kc times RT delta N gas. Okay? Kp is equal to Kc RT delta N gas. It's basically PV equals nRT, because if I write this like so, okay, and I bring V over here and I write in terms of pressure, this is molarity right here. And since that's due to concentration, it's basically that formula. Okay? But, we're going to use this formula. So what do all these variables mean? Well, Kp, again, constant. Kc, constant. R is your ideal gas constant, the 0.0821. Okay, now we're back to this one. We use the other one in the kinetics part, liters, atmospheres per mole Kelvin. Therefore, my T is my temperature. It has to be in Kelvin. And then our delta N. Our delta N gas is the difference in the moles of gas. Moles of gas. Moles of gas. Moles of gas. I don't know how many times I'm going to say it. Moles of gas. Products minus reactants. Moles of gas. What is the change in the moles of gas? Products minus the reactants. The moles of gaseous products. The moles of gaseous products. Not all the products. Just the gaseous products. Moles of gaseous products minus the moles of gaseous, only gaseous reactants. Okay. So if I were going to use this formula in this equation, or for this equation up top, given that information, okay, so I want to know what Kp is for this reaction up here. Moles of gas. Moles of gas. All right, I want to find Kp. So I'm going to write out my formula. Kp equals Kc RT to the delta N gas. Okay? Now, I'd have to be given something else. I'd have to be told, let's say the temp is, 298 Kelvin for this reaction. If I want to find Kp, I plug in my Kc, 2.2, times 10 to the second. I plug in R, 0.0821. 1. Multiplied by the temperature, 298. And now I have to find my change in the moles of gas. Products minus reactants. Over on the product side, there's 3 moles of gas. Over on the reactant side, there's 3 moles of gas. My delta N of my gas in this is going to be 3 minus 3, which is 0. Now this is important. If there is no difference in the moles of gas on the right-hand side to the left-hand side, then Kp equals Kc, because anything raised to the 0 power is 1. So this would cancel out to be 1. So my answer for my Kp would be the same exact thing. 2.2 times 10 to the second. I mean, you could put the math into your calculator. Put the numbers in and do the math, I should say, in your calculator. But you're going to end up with it being essentially 1 there. Okay. Questions on that? We'll try another one. I'll start making up one while you think if you have any questions on that. All right. 2a solid plus 2b solid liquid. Let's make it a liquid. L. That's terrible. There is no units, Orlando. It's just assume that if it's Kp, it's atmospheres, and if it's Kc, it's concentration. But there are no units. It's just assume that if you're finding Kp, you're using atmospheres, and if Kc, you're using molarity. All right, so let's look at this one. We want to find Kp. So Kp again equals Kc RT delta N gas. (1.1 times 10 to the negative second) is our Kc value. We know what R is. Okay, 0.0821. I need a temperature, I don't know. Let's just stick with the 298 Kelvin. We would be told that. 298. And now we need our delta N. So, this is an S. That's not a G, it's an S. Okay? So we look at it. Now, this is the delta N of gases. So on the right-hand side, I have 2. On the left-hand side, I have 2 moles of a liquid, 2 moles of a solid. I have no gases. If there's no gases on either side, then it's 0 minus 0. If there's no gases on one side, it's minus 0. So it's 2 minus 0. So my answer will be taking the ideal gas constant, 0.0821, multiplying it by the 298, squaring that answer, and then multiplying it by the Kc, 1.1 exponent negative 2. And I get, for my Kp, if I did my math right, 6.58. Obviously, yes, no, it's plus negative numbers. You are correct. I'm actually adding a negative 0 there. Touche, Orlando. Touche, salesman. So that PowerPoint's a little off the screen there, but there it is, summing up essentially what we just talked about. This slide here is showing you how it's been derivated. or found where it all comes from. And there's a couple problems here for you to try for homework. Sample problem 17.4. Okay. They want you to find the KC, they give you the KP, and they want you to find the KC. Okay. So try that one for homework. And then on top of that, I want you to try Let me see. I'm going through the numbers here, just make sure. All right. You treat KP just like you treat KC, and you just like you treat QC. I mean, if you want to say there's a QP, there technically is. Okay? There technically is. So we're going to look at page, I don't know why I grabbed the purple one out of all of them here. Page 786. 17.28 to 17.38. I actually grabbed this, Brady. I actually grabbed this morning and had it sitting there. So I actually buried it away on my desk here, on my table, if you will. I actually did that. Alright, guys, so that's the end of the lecture, but we'll keep the stream going. If you have questions, comments, complaints, just want to chat.